The artificial intelligence industry spends billions of dollars and countless compute cycles trying to erase the machine. Engineers constantly tweak response times, pitch, and phrasing to make their models sound less mechanical and more organic. But when we optimize for a human-like interaction, we rarely stop to ask whose version of humanity is being used as the baseline. What the industry calls human-like is actually a highly specific, narrow set of social behaviors. This creates a system governed by neuronormativity, the assumption that there is only one standard, typical way for a person to communicate. This curve plots how AI design shifts from straightforward, code-based outputs on the left to highly emotive avatars on the right. As models learn to simulate empathy and mimic social nuances, developers track a corresponding spike in broad user engagement. Yet, as that engagement line climbs for the majority, a secondary metric tracking divergent users drops sharply, creating a distinct blind spot in user experience. Neurodivergent communication styles, including traits frequently seen in autism and ADHD, often prioritize direct information exchange, literal interpretation, and consistency over layered social performances. These preferences run in direct opposition to the neurotypical baselines of enthusiasm, varied tone, and implied meaning currently hard-coded in major AI models. By actively designing systems to eliminate anything categorized as robotic, developers are implicitly pathologizing the natural ways autistic people communicate. This friction is visible in recent empirical research documenting the impact of AI on neurodivergent populations. A 2025 study from the ACM Conference on Fairness, Accountability, and Transparency examined the specific design intents of engineers building human-like AI. Simultaneously, policy research from Aotearoa, New Zealand, evaluated how these same algorithmic biases generate specific workplace risks. Together, these findings point to a structural problem. When we optimize for a narrow definition of humanness, we risk building exclusionary barriers directly into our technical infrastructure. To understand how this happens, we need to look at what developers actively try to filter out of their systems. This pie chart breaks down the exact traits that cause an AI to be classified as uncanny by the researchers building them. When combined, communication styles and emotional expression account for over 60% of the behaviors developers flag as unsettling. This tree map categorizes the specific behaviors developers label as undesirable and aim to suppress across their models. Traits categorized as inappropriate tone and repetitive carry heavy weight, and engineers actively police these patterns to prevent user frustration. The data shows developers operationalize their definition of humanness almost entirely by eliminating interaction styles they personally find uncomfortable or abnormal. These abstract labels of undesirable behavior translate into specific, real-world conversational choices. Look at these direct quotes from developers who describe the use of numbers or repetitive text-only responses as unnatural, odd, or overly robotic. In psychology, there is a concept called the double empathy problem. It posits that communication breakdowns between autistic and non-autistic people happen because of differing social norms, not because one group possesses a biological deficit. What developers measure and penalize as robotic is a mathematically precise and socially valid form of human communication. The traits these engineers aggressively suppress, such as exact repetition, literal interpretation, and a flat emotional tone, align directly with natural autistic communication profiles. Studies consistently show that autistic users frequently prefer interacting with non-anthropomorphic, direct, text-based interfaces. This preference is rooted in sensory processing differences and a desire for clarity, rather than navigating the cognitive load of simulated social cues. When designers add perky dialogue or eloquent phrasing to avoid seeming like a machine, they force users to navigate a neurotypical social convention just to extract information. Labeling straightforward, literal communication as dysfunctional in an AI model inevitably dehumanizes the actual humans who communicate exactly the same way. The uncanny valley in AI design is frequently a measurable technical reflection of the industry's underlying anti-autistic bias. This massive cognitive accessibility gap persists because of how modern AI pipelines are structured. In the FACACT research, developers explicitly admitted that neurodivergent populations were completely outside their area of expertise. While physical accessibility features, like screen readers, are sometimes factored into early design phases, cognitive accessibility is routinely ignored. A strict mindset divides the workflow. Machine learning engineers focus purely on models, operating under the assumption that accessibility is solely the responsibility of the user interface team. This compartmentalization allows engineers to tune their models toward neurotypical norms without ever confronting the exclusionary impact of those choices. The development pipeline structurally insulates engineers from the ethical implications of cognitive exclusion. This bias becomes dangerous when it leaves the chatbot window and scales across a company, increasingly embedded into workplace management and performance monitoring systems. They constantly ingest data on employee productivity, communication frequency, and behavioral patterns. This introduces the issue of psychosocial safety, the legal and ethical requirement to protect workers from psychological harm, including algorithmic surveillance. Neurodivergent workers rely on reasonable accommodations, like specific communication formats and flexible workflows, to thrive. But algorithms are trained to expect uniform, standardized behavior. This network diagram illustrates what happens when specific user nodes are measured against that baseline and flagged due to mismatched communication data patterns. If an autistic worker relies on rigid, scheduled communication, the algorithm scores those literal, direct inputs as an at-risk behavioral anomaly. If an ADHD worker demonstrates variable attention, producing intense bursts of work followed by breaks, the timing inputs are scored as low engagement. This creates a disclosure trap. Workers who hide their neurodivergent identity to avoid workplace stigma are still identified and flagged by the algorithm's behavioral baseline. The system has no context for the divergence. It only has the capacity to measure the deviation and punish it. Constant surveillance against an impossible standard generates severe stress and exacerbates the already high underemployment rates among neurodivergent populations. When conversational bias scales to the enterprise level, it weaponizes neurotypicality against the 20% of the workforce whose neurology diverges from the mean. Despite these measurable harms, the current regulatory landscape offers virtually no protection. In Aotearoa, New Zealand, the Health and Safety at Work Act imposes general duties of care, but is structurally unfit to govern AI-specific psychosocial risks. International instruments like the United Nations Convention on the Rights of Persons with Disabilities and the European Union AI Act establish stronger benchmarks, but these are rarely translated into enforceable domestic law. Current public service guidelines for responsible AI remain strictly advisory, and their definitions of fairness are still heavily framed around neurotypical baselines. Defining human-like behavior by neurotypical standards hard-codes a specific psychological profile into our digital infrastructure. This transforms a conversational quirk into a permanent systemic barrier. Building truly ethical artificial intelligence requires integrating the full spectrum of human neurology as a core architectural requirement.